3 times 10 to the 8th meters per second. V is the speed of light in the medium we are looking at. So if we're looking at glass, V is the speed of light in glass. If we're looking at water, V is the speed of light in water, right? So you always know what C is because it's always 3 times 10 to the 8th. And they'll give you, say, a V, right? What the speed of light is in the medium you're looking for. And you could find the index of refraction, the N value for that medium, right? You can also see that there can ever be an N value less than 1 because nothing can be, if you're looking at C over V, if you had an N value less than 1, that means V is higher than C. That means light is faster in actually that medium than it is in a vacuum, which is not possible. Light is always fastest in a vacuum. So you can never have an N value less than 1. So if you did a calculation and it's less than 1, you know you did something wrong and you should redo it. We consider air to be essentially a vacuum, so N is in air is also 1, since C and V are the same, right? That's about it. Just using N equals C over V and this equation, N1 sine theta 1 and equals N2 sine theta 2. You should be able to answer almost any refraction problem. Okay. All right. Well, we mentioned the theta is with respect to the normal, but what happens if theta is actually greater than 90 degrees, right? Because the normal is a vertical line, and then the boundary, which is the area that separates air from water or from the two, whatever the two substances are, is perpendicular to it, right? It's like this, and you can see it right here. What happens if the theta is actually greater than 90 degrees? And you can see that right here. This is what we were just looking at, a normal line, just changes like that. This is what happens if it's 90 degrees. And what happened in this case is actually you wouldn't see it. So going back to the example of the pencil in water, put a pencil in a glass of water, you can see it, it's just crooked a little bit. If you have 90 degrees, you put the pencil in the water and you can see it about in the air. But as soon as it goes in the water, you can't see it anymore. All right, because none of the light is shining through. Okay, so it's 90 degrees. If you go above 90 degrees, say 110 degrees, you have something like this. And this is called total internal reflection, right? What it just means is that none of the light is able to refract. All of the light just gets reflected right back at you from the medium you're going to. Total internal reflection can only happen when you're going from a higher medium to a lower medium. So say water to air or glass to air. It can never happen when you're going from air to water. The reason for that is actually because when you're going from air to water, like I mentioned, from a lower index to a higher index, the angle actually has to decrease, right? So if you have an angle of 30, it would decrease. It can't increase past 90. Whereas where you're going from a higher index like water to air, the angle can actually always increase. So it goes from, say, 70 to 90 or from 80 to 95 or something like that. And that's when you get total internal reflection. It can only happen when you're going from a higher index substance to a lower index substance like water to air or glass to air or something like that. Right, and again, total internal reflection is when the angle, the theta 2, between the normal and the ray that's coming out, the resulting ray, is over 90 degrees. And what you get is actually something like this, where rather than coming out crooked, it actually doesn't come out at all and it reflects back, right? Say like this angle is, say, 120 degrees, right? And it doesn't come out of the, like it was going from the water into the air. It actually doesn't come out of the water and you can't see it when it comes out. It just goes back in to light and you wouldn't be able to see it in the air. Okay. Essentially, the light gets trapped underwater. Next, I want to talk about reflection a little bit. This is very basic reflection. Apart from refraction, there's also reflection. Any surface can be and is reflective if it is also refractive. So refraction and reflection happen all like together all the time. If you even want to look back at this, You see, this is the classic example of refraction, right? Going from here to here. But you also notice this like light blue line right here. This is reflection, right? So this light ray is being refracted, but at the same time, the same light ray is also being reflected, right? They happen simultaneously, okay? And in the case of total reflection, there's actually no refraction, there's just reflection, right? But most of the time, when you have refraction, you also have reflection, right? Reflection is very easy to calculate for just a linear surface. So for example, like the boundary between air and water is a straight line, horizontal line. The angle of reflection is always the same as the angle of incidence, right? So you're coming in at θ1 this way. Reflection is exactly the same. You're going out like this. The angle is also θ1, just like this, right? Reflection, the angle coming out is always the same as the angle coming in, right? But you also have reflection or refraction, which has a θ2, which is a different theta. And the reason reflection is the same as coming out is the same as coming in, because you do n1 sine θ1 sine θ1 equals n1 sine θ2. What's θ1 and the θ2? Well, if n1 is the same here and here, that means sine θ1 is the same sine θ2. So that means the angles have to be the same, right? Very simple to figure out mathematically, but even simpler, just remember reflection, same angle, okay? Before I move on, let me answer some questions that people may have in the chat. So if you have any questions, please put it in the chat. Somebody asked what happens when it's at 90 degrees, right? So again, when I said it's at 90 degrees, it's still, you still have reflection, right? However, it doesn't come out of the water, so it goes parallel along the water, but it just doesn't come out. If you're looking sideways, so if you're looking at it like this, right? If you're looking at this pen and I dipped it half in water like this, you would be able to see this water portion, but you wouldn't really be able to see the light that's coming out on the air portion, right? Right. So what's making the angle increase? So internal reflection, like I mentioned here. Sorry, let me go back. N1 sine θ1 is N2 sine θ2, right? If we're pretending N1 is water, 1.3, and N2 is air, which is 1, right? This sine θ1, it has to be, say this is 5 or something. I'm just like giving you an example just so it makes sense, right? 1.3 times 5 is whatever, right? 1.3 times 5 is some number. If I wanted to get that same number multiplying by 1 here, would this number have to be 5, less than 5, or bigger than 5 in order to get the same thing as this, right? In order to get, I don't know, 7 or whatever this is equal to, right? This would have to be, yeah, this would have to be greater than 5. It would have to be like 7, right? So that means if you're going from a substance that has a higher N1, say water, into a lower one, say air, which has 1, so going 1.3 to 1, you know that the angle goes from 5 to 7, right? If the index decreases, the angle increases. If the angle of incidence going from water to air was 80, the resulting angle could be 90, could be 100, right? It has to be bigger than than the 80 that came in, right? And if you go the other way, the opposite thing happens. If you go from air to water, it goes from smaller to higher index. That means a higher angle goes to a smaller angle. The angle decreases, going from 30 to 20, 40 to 30, or something like that, right? Does that make sense? Right. And there is the difference between angle of reflection, angle of incidence. Angle of incidence is the one that goes in. Angle of reflection is the one that gets reflected. The angles are the same, right? The value of the angles is the same. Okay, last question. Somebody asked, why can n never be less than 1? Right? The equation for n is c over v. You know that c is the speed of light in a vacuum. V is the speed of light in whatever medium it is we're looking at, water, glass, air, whatever. In order for n to be less than 1, that would mean that V is bigger than C, right? That would mean V is bigger than C, the denominator is bigger than the numerator. Well, the speed of light in any surface, water, air, glass, anything, it can never be bigger than the speed of light of air in a vacuum in no substance, right? Speed of light in a vacuum is like the fastest thing you can have, right? So that means the speed of light in any other medium would be lower, right? Or at most, it can be the same. So that means that's the smallest value n can be is 1. It can never be lower than 1. Because that would mean, yeah. All right. So I actually want you guys to try this question, going over a lot of the stuff we just mentioned. And let me start the poll. Okay. So please take a couple minutes to answer this. Okay, please take another 30 seconds or a minute to answer this question. Okay. I'm gonna end the polling. So 80% picked A, right? Which is the correct answer. The angle of reflection is 60 degrees, which I'm very happy about. Like I mentioned, the angle of incidence you have to know is the angle that it comes in at, right? For reflection, the angle it comes in at is the angle it comes out at. So 60 comes in, 60 comes out. That's it. Angle of refraction is 60 is not true because so refraction follows the n1 sine theta 1 equals n2 sine theta 2 rule, right? So the only way for the refracted angle to be 60 degrees would be if the two surfaces, air and water, had the same n value, but they don't. The index refraction of air is 1, water is 1.33. So it would actually, the angle would decrease, right? I don't know what it would be. It would be like 50 maybe, but it would be less than 60, right? Total internal reflection would occur. Again, this is not true because total internal reflection only really happens when you go from a higher index substance to a lower index substance. So if we were going from, say, water to air, that may happen, even though it likely wouldn't because 60 degrees is too small of a number. But it may happen if we were 80 degrees, if we're going from water to air. From air to water, the angle would actually decrease, right? Wouldn't be above 90, it would actually be below whatever it started out. So it'd be below 60 or below 80 or whatever we started off with, right? So that's why C can't be true and D is, yeah, because C is not true, D is not true. Okay. This is, that's the majority of light and optics that you'll have to know for the MCAT. There is one other section that I do want to cover, lenses and mirrors. this is the hardest. I think this is the most complicated and hardest section, even though it's not like too much harder. There's just a lot to it. Luckily, it's also the one that's tested the least, right? So if you don't understand it, of course, try, but it is what's tested the least. So at least you have that going for you. But I think you should still know it, because just in case it is tested, I think it's important that you understand this, because especially if you want to go in med school, what's the most common lens that we have? Other than the one I'm wearing, my glasses, the most common lens we have is actually our eyes. Our eyes act as lenses, so you should really know how those work, right? So this is actually something that could be relevant to medicine, right? Unlike some of the other physics that we cover. Okay, so there's two types of lenses and mirrors. There's concave and convex, which have different properties. I'll be talking about mirrors first, because I think that's a little bit easier, and lenses afterwards. There's a lot of similarities, but there's also some differences between them. So keep in mind, first I'm talking about mirrors, not lenses. For mirrors, concave is converging and convex is diverging. Remember those two words, converging and diverging, and how they relate to mirrors. So concave is converging, convex is diverging for mirrors, because for lenses it's going to be the opposite. But for mirrors, at least this is how it is. This is what a convex mirror looks like. It's round, right? And a concave is rounded in, right? And concave, imagine it's concave in, so it's like looking in a cave, right? It's hollow. Whereas convex is the opposite, it's rounded towards you, right? It's like circular. Okay, and you can actually see what I mean with the converging, diverging. Look, it hits like this and then bounces off, so it diverges, goes from like this to out, so diverges, whereas concave hits it and then goes towards each other, or converges, for mirrors at least. First, there's some variables that I want you to know. These are a little bit, there's a little bit much to here, but just try and follow. F is, first variable is F, the focal length, right? I could explain exactly what the focal length is in detail, but most of the time, they'll just give you a number for the focal length and they'll tell you what the focal length is, or they'll ask you to find the focal length. You don't have to really like know specifically what it is for, and for the purpose of the MCAT, they'll just give it to you, right? Or they'll point it out on a drawing, right? Somebody put it in the chat that, yeah, that's about what it is, but I don't want to get too deep into that because it's not necessary. O, which is important, is the distance from the mirror to the object. So O, object, right? It's the distance from wherever you're standing to the mirror, right? I is image, the distance from the mirror to the image, right? Those are very self-explanatory, okay? And by the way, object and image are not always in the same spot. Most of the time they won't be. And this is a very good equation to add these three variables to each other, right? 1 over O plus 1 over I equals 1 over F, right? And this is the first step to almost any lens and mirror problem, right? The first step to almost any lens and mirror problem is going to be finding either F, I, or O using this equation and the two variables that they give you, okay? They may give you O and I, and you have to find F. They may give you I and F, and you find O, whatever it is. This is the first step to almost any lens and mirror problem. An easy thing to remember is that if F is greater than 0, the mirror is converging. If F is less than 0, it is diverging. And when I say it's an easy thing to remember, I remember that you should. I want you to know that you should remember it if you, just because it'll be easier to figure out a lot of things doing this, right? And I specifically use the words converging and diverging rather than concave and convex, because this rule actually applies. This rule is always true for both lenses and mirrors. If you remember, I said concave and convex are different for lenses and mirrors, but this rule is the same for both, right? So if F is greater than 0, if F is positive, the focal length is positive, it's always converging. Lens or mirror, it's always converging. If F is negative, it's always diverging. Lens or mirror, it's always diverging. Okay, so that's how I want you to remember it. So real versus virtual image. There are real images and there are virtual images. For a mirror, if the eye, which is the distance from the image, from the distance between the image and the mirror, is positive, it's a real image. If I is negative, it's a virtual image. And I'll cover in a bit what positive and negative I mean, right, where it is. But if you want to think of it like in real life, I would say a real image versus a virtual image. A real image, and this isn't like the physics accurate way to describe it, but it's just a way I remember it. The real image is where you expect the image to be. So, for example, if you're looking in a mirror, right? Pretend this phone is a mirror. This phone is a mirror, right? If you're standing here in front of the mirror, you expect that the image will go here and then it'll bounce back and it'll be like reflecting back on you, right? When it goes into a mirror, you expect it to go like this and then bounce off and to be on the same side as the object. So you expect that the image and the object are on the same side as each other when you're looking at a mirror, right? And if that's the case, then it's a real image. However, this is not always the case, right? Sometimes the object is here, it goes into the mirror, and actually the image actually shows up here behind the mirror, right? You still see it, but in your vision, it's actually behind the mirror, right? If that's the case, it's a virtual image, right? And remember, this is for mirrors. For lenses, it's opposite again. But for mirrors, that's the case. If it's on the same side as you, it's a real image. If it's on the opposite side, it's virtual. Okay. So somebody asked in the chat, is it true that virtual images can be projected on a screen? I'm not actually sure about that. Yeah, you would have to look that up because I'm actually not sure, right? Yeah, that's something like, that's like an extra bit of information, right? Okay, next we want to talk about magnification. Magnification is another important quantity, and this is the other, I would say the only real other equation that you would have for lenses and mirrors is magnification. M is equal to negative I over O. So I, again, is the distance from the image to the mirror. O is the distance from the object to the mirror. O is always positive, by the way. 99% of the time, O will be a positive number. Whereas I mentioned I could be a negative number or a positive number, right? And the equation is M equals negative I over O. Don't forget this negative right here, right? So if I is negative, then it flips and M is actually positive. If I is positive, this flips it, becomes negative, M is negative because O is always positive. Okay. Okay. Then if M, okay, now I want to talk about M. If M is a negative number, then the image is upside down. If M is a positive number, the image is right side up. So this is also an important note. M can actually tell you a lot. First, M, as you may think from magnification, it tells you if the image is enlarged or reduced compared to the object, but it also tells you if the object is right side up, if the image is right side up or upside down. If M is negative, then the image is upside down. If M is positive, the image is right side up. Okay. And now for magnification, if M is greater than 1 or less than -1, or if the absolute value of M is greater than 1, the image is bigger than the original object. It's scaled up, right? So if you want to think of it as a scale, 1 being 100%, if it's greater than 1 or less than -1, the magnification is 110%, 150%, 200%, or something like that, right? However, if M is a decimal smaller than 1 or smaller than or bigger than -1, or like, yeah, the absolute value is less than 1, the image is smaller than the real object, the original object, so it got reduced. right? And that's if you had like a zoom and you like, or if you had a magnifier and you just went like 75%, which is 0.75, or 50%, or 25% and made it smaller. If you want to think of it like that. Okay. Next, I want to talk about lenses. So lenses have the exact same formulas as mirrors. So m equals negative I over O. And this main equation, they're the same. The only differences between lenses and mirrors is in lenses, converging is convex, diverging is concave, right? If you remember from mirrors, it was the opposite, but here converging is convex, diverging is concave, right? But the rule with a positive f being converging and a negative f being diverging still applies. All it means is if you have a positive f for a mirror, it's concave. If you have a positive f with a lens, it's convex, right? But it's still converging both ways. And negative f is still diverging both ways, okay? Next, when I was talking about images, right, being real versus virtual, again, it's the same thing as in mirrors for lenses, right? Positive I is still a real image, and a negative I is still a fake image. Sorry, whoever that is, mute. Thank you. Okay. And a negative I is still a virtual image. But, however, now the locations are different. So, like I mentioned before, if you had a mirror and you had a person, you expect that for a real image, you expect that it goes to the mirror and then it bounces off and the image will be produced on the same side as the object, right? Because mirrors reflect, right? And that's how you know it's a real image. With lenses, it's kind of the opposite. If you want to think of it this way, and this is how it helps me, but it's not actually like exactly physics accurate, but it's just a helpful way to think about it. If you are standing on this side and then there's a lens here, say like a glass wall or some kind of lens, right? Where you would expect the light from you to travel this way, and then actually rather than reflect like in a mirror, you'd expect it to go through, right? And you'd expect the image to be here, right? On the other side of the lens, right? And that's what a real image is for lenses. Unlike in mirrors, you don't expect it to reflect, so you expect it to go through, and it would have to be on the opposite side of you to be real. Whereas if it does reflect and go back onto the same side as you for a lens, it's actually a virtual image, right? Again, it's the opposite as in mirrors. Okay, and I will show you a picture here as well. This is what a concave and a convex look like, right? And somebody want to ask for pictures, right? In a lens, so say this was a person, and the person is the object, right? So I'll put an O here, object, right? And you have say a convex mirror, convex lens. This is a lens, right? What I was saying before was you expect the light from you, the object, to travel this way, reach the lens, and then continue traveling this way. And then there would be an image, which I'll just draw as a big I, an image formed right here. Notice how you and the image are on opposite sides of the lens, right? This is real. If instead, back to the person, the object, and then the lens, right? The light travels from you to here, and then actually bounces back. And then the image is right here behind you, right? This is the image is on the same side of you from the lens, which is not what you would expect, and it's virtual. Right, this is virtual. Whereas for a mirror, right? This is say a mirror, again, person is the object, right? You expect that it hits the mirror and comes back, and now the image is on the same side as you, because mirrors we expect reflect back, right? And just like we would expect, the image is on the same side as the person, so now it's real for mirrors. Whereas if it were to go through and the image were focused here on the opposite side, it would be virtual. Okay, does that kind of help explain it a little bit? Right. Converging, diverging. Let me just write that down again. Oh, actually, it's written here. For lenses, convex, converge. And concave is diverge for lenses. For mirrors, convex, diverge. Concave, converge, right? Again, you can see that in the way the light works here in this picture. So the light rays are coming in like this, and then once they hit the convex lens, they all bunch up to each other. They converge to each other. Whereas here, they like this, and then they go out, so they diverge, right, from away from each other. In a concave lens, they diverge from each other, right? Whereas here, convex, which was converging for a lens, they hit the mirror and then they bounce off away from each other, so they diverge from each other. Whereas a concave mirror, they go towards each other, right? They go towards each other, so they converge. Does that make sense? Okay. Any questions before I move on to our poll question of the day? Okay. Let's start the poll. Okay. This one's a little bit more complicated and it does involve some math. I'd highly recommend using like scrap paper or something else you have. Again, remember I said that 1 over O plus 1 over I equals 1 over F is essentially the first step in almost any lens or mirror problem. That's always the first step. So try and see if you can do that, right? And the other important equation that I said to know was M equals negative I over O, the magnification equation. Those two equations will pretty much be, with those two equations, you're pretty much able to solve any mirror lens problem. All you have to know is just some other stuff, right? How they relate to each other. What does some wording mean? What is a convex lens in this case? It's a converging, diverging, right? Okay. Okay. So I'll give you guys a couple minutes. Okay, I'll give you guys another couple minutes. Actually, another like 30 seconds a minute. Okay. Okay. I'm gonna end the pollen. So the answers were pretty split. The most popular answer is actually that you don't know, right? So this says that people really were a little bit confused, and that's fine. And I'm happy to go over it, right, in depth, right? This is a little bit of a complicated question. I said this topic was a little bit hard as well, right? So first thing you want to do, write down what you know. So an object is at a distance of 3 focal lengths from the center. So that means O, which is the object distance, is equal to 3F, right? Well, you know that F is equal to F, and you know that O is equal to 3F. Now you have 2 of the 3 variables that I said were for the main equation, 1 over I plus 1 over O equals 1 over F, right? We can erase 1 over O, I mean, and then replace it with 3F, right? Because we know that O is equal to 3F, right? The reason we know that is because it said object O is a distance of 3 focal lengths, right? Okay, now we want to rearrange this, so like terms on the same side. Subtract this from both sides, subtract this from both sides, you can rearrange it. 1 over 3F. Or actually, it would be easier if I subtracted this from both sides. So we do that. 1 over I is equal to 1 over F minus 1 over 3F, right? Doing a simple subtraction with fractions, if you guys remember, get like terms in the denominator. So multiply this by 3, multiply this by 3. Now you have 3 over 3F, which is equivalent to 1 over 1F, right? Minus 1 over 3F to get 1 equals 1 over I. What you get when you do this is just 2 over 3F is equal to 1 over I, right? If we're trying to find what I is, all we simply do is just, we can cross multiply if you have more complicated numbers. In this case, you can actually just flip it, but let's just cross multiply just so you guys see it. Cross multiplication is like this. So I times 2 is 2I. 1 times 3F is just 3F, right? Divide both sides by 2 to isolate I equals 3F over 2. We found out what I is, we know what O is, and we know what F is. We want to find what is the ratio of the height of the image to the height of the object. What does that sound like, ratio of height of the image to the height of the object? Well, that sounds like magnification, right? What's the ratio? Like what the ratio is what the magnification is, right? So what they're actually asking you is, what is the magnification, right? Magnification is equal to 3 over 2I. But since we don't care about if it's upright or inverted, since we don't care about that, we actually don't have to put the minus sign, right? Magnification is usually M equals negative I over O. Since we don't care about what the sign is for M, it's positive or negative, all that determines is if the image is upright or upside down. Since we don't care, we don't have to do that. We're just doing I over O. I is 3 over 2F, right? O is 3F. Simple, now it's just simple division. F cancel out. 3 over 2 divided by 3. So I can actually just multiply by 1/3, right? Multiply. The way you divide fractions is you change the sign to multiplication, flip the fraction. So 3/1 becomes 1/3. 3 cancels out. All you're left with is equal to 1/2, right? So the answer is C, 1/2. Okay. Now, you guys get that from the first round, or do you want me to go over it again, or which part do you want me to go over? Okay. Yeah, some people are saying there's no way I would do that in a real exam. So really, like, if you have the time, and like I mentioned, these types of questions are rare, right? But if you have the time in this section and like you don't see that right away, but obviously skip it because it's going to take some time to do some math and like do a lot of like changing, right? A lot of algebra. But if you have the time, think, what do you know? Well, you know what O is. It's equal to 3F, and you know obviously F is equal to F, right? You know and I told you there's 3 main variables to any lens mirror problem. There's 3 main variables and 1 main equation, right? You know 2 of those 3 variables. That means you can find the 3rd variable, which is I. Okay. Yeah. Yeah. Them asking for the magnification versus the height ratio is the same thing. Yes. Magnification. So the ratio of the height is just how big is I compared to O. Well, that's exactly what magnification is. How much bigger is I compared to O? Or how much bigger is the image compared to the object, right? It's 1.5 times bigger, or it's 1.3 times bigger, or it's, in this case, it's actually 0.5 times bigger, which is half the size, right? Again, yeah, yeah, the F's can cancel out because look, you have F is a number. F is like a focal length, right? It's like maybe say like F is 5 or something. If you had 5 in the top and 5 in the bottom, just like if you had like 3 in the top, 3 in the bottom, you cancel them out, right? Just simple algebra. Okay. Yeah, ranging math is like important for this, especially ranging math is very important. As you can see, like most of this problem is actually just doing algebra, and like if you don't know how to use like fractions, which is like seems like simple, like fractions we learned that in 6th, 7th grade, but like you learned it in 7th grade, but then you didn't use it for another 6, 7 years, maybe even longer if you took breaks from 6th, 7th grade, right? So yeah, so remember what like how math works and how fractions and algebra and stuff you have to remember. Okay, so again, with any lens, or if you guys have any questions, keep putting in the chat and I'll keep answering them. But yeah, the main equation in all lens problems, 1/I plus 1/F plus 1/O is equal to 1/F. This is the main equation. This is the first thing you do. The other equation is this one, M equals -I divided by O. If they give you a lens or mirror problem, know that you're using one or both of these equations, and then just look at which variables that they're giving you and which variables they're asking you for, right? Another key thing that I actually didn't mention this problem and actually didn't come up in this problem just based on pure luck. They asked for a convex. They said this was a convex lens, right? Remember that a convex lens means it's converging. For a converging lens, for a converging anything, lens or mirror, converging means F is positive, or F is greater than 1, or F is greater than 0, I should say. F is a positive number. If they said instead, it was a concave lens or a convex mirror, something that was diverging, you would actually have to do a negative f, right? So O is 3f, but f is actually negative f, right? I know that doesn't make sense, but like the f is actually negative f. So you would have to do equals negative f, then 3f, or so, and then it would be on this side, it would be negative 3, like negative 3, right? And it changed the problem completely, right? If they just simply said concave lens or converging mirror or something like that, right? So pay attention to that as well. In this case, it's not. F is just positive, so you don't have to make any changes, but that was just like luck. Yeah. Yes, half is less than 1, right? So the image, the ratio of the height of the image to the object, the image that you get as a result is actually half the size of the object, right? It's smaller. So m is 1/2. So the image is actually smaller than the object, right? It actually shrunk. So they wouldn't ask, the only time they would actually ask for height, they wouldn't ask you height in inches. Well, actually, they might, but you use this. Magnification, it's not magnitude, it's magnification, right? Magnification is a ratio. Magnification is the ratio of image to object, right? So, for example, half. The image is half of the object, or if it was 2, the image is twice as big as the object. If they then told you the object is 3 centimeters, the image is twice as big as the object. So the image is 6 centimeters, or it looks to be 6 centimeters. Yeah. So you would first find the magnification, which is a ratio. And then based on that ratio, then you might ask to find the specific height, which is 3 centimeters, 6, whatever. Yeah, you get what I mean. Yeah, so like I mentioned, this is the hardest thing you can find in optics. By the way, this is the last slide. So I'm not going to delete anything, but this is the last slide. But so we are done after this if you guys want. But I will be sticking around for more questions. Somebody asked in chat, some texts define 2f as radius of curvature. Yes. That's something I didn't write. I didn't like bother talking about because it's just so rare and so very specific that you'll, in all likelihood, you'll never even see it. But there is a thing, and I didn't want to confuse you more, but yeah, there is a value called R, I believe. Yeah, is R F is equal to R over 2, I believe, or 2R. No, it's either 2 over R or R over 2, right? One of those two. I think it's, I'm gonna just double check just to make sure before I say something wrong. 1 second. Yeah, F equals R over 2. This is correct. So this, if you guys stuck around, F is also equal to this value called R over 2. I'm not even gonna like really, I'm not, you may see it, but if you do see it, they'll just tell you R, and then you'll just be able to plug in R. That's why I didn't bother telling you what focal distance really actually is, right? You don't know actually, like if I drew you a diagram, you wouldn't really know what it is. Same thing with R. If I drew you a diagram, you wouldn't really know where it is, but just know that there's this value called F and there's this value called R, and this is the relationship between them. And F is equal to R over 2. Okay. Any other questions, or can I move on? About this, anything we covered today or anything? Okay. Well, if that's it, if there are no more questions.
Yes, quick question, Mark. Do they ever ask us about microscopes, you know, when you have those double One lens in front of another one. Will they ever do that to us?
Oh, okay. I was gonna say, microscope is technically just a lens, right? But if there's multiple lenses, they may ask you about multiple lenses. Actually, what
Well,
you have to
yeah.
what you have to do, it's exactly the same as this, right? Except the image. So you have the first lens. There's an object, and the first lens produces an image from that object, right? And then the second lens uses that image as the object and then produces a second object, a second image, right? Right. So the resulting image from lens one is the object for lens two. So all you have to do is just do exactly what I did for the last question, except do it twice, right?
So we still use those equations, those images.
Same equations, same everything, same rules. Everything is the same, except you just do everything 2 times, right? And then the second object is just the first image, and then there's the second image.
Thank you.
No problem. There's also, if you're really going deep, there's also lenses that aren't, like when we do this, we assume the lens is like paper thin, right? It doesn't have a thickness. There's also, I'm not going to go over it, but there's, it's very rare, but there are lenses that are not perfectly thin, right? Like not paper thin, they have a thickness to them, right? And that just factors into a little bit into the equations and changes them a little bit.
Okay, Mark, I have another question. When they ask question about hyperpia and myopia, one is nearsightedness and farsightedness, and which lens?
Right, yes.
Can you go over that a bit?
Oh, okay, yes.
One second. Let me just.
So the difference between that is converging and, oops, sorry.
Yeah, if you can just go through that, right?
I would, I'm thinking, I think I would prefer do that if we do maybe like, let me just check the schedule. I believe we are doing vision for one of the lectures, and if we do, then we're doing that for vision. But I'm going to double check just to make sure before I say anything, okay? If not, I'll go over it right now.
Yeah, because the question is the image formed before the retina or after the retina, and which lens?
Oh, we are actually are doing vision and hearing tomorrow, actually, right? Okay. So yeah, we're doing visual pathways tomorrow, and Janelle put in the chat as well. We're doing visual pathways tomorrow. So save that question. We'll do that question tomorrow. Right. But the principle behind that is basically, it's actually similar to what I was talking about, the double images. So the light, if you notice here in a lens, it has to like converge onto this like point, right? Right. What happens in people that have like bad vision is that it actually doesn't. It converges at a point maybe here or maybe here, right? And that's what determines nearsighted or farsighted. It doesn't actually converge where it's supposed to converge, and so you're not actually seeing things in focus because they're at a different point. They're converging at a different point. So it's essentially like if you know in a camera where there's like the thing that's in focus is like clear and then everything else is blurry. Well, if you have bad vision, everything is in your eyes, everything else is everything else, right? Because it's all blurry because it's all out of focus because it's not actually lined up in focus. And all lenses do, all like the glasses do, is they just add in a second lens that will move it either like closer or further depending on, and do it like that, right? And you would need like concave versus convex lens to do to move it differently.
I could wait for that lecture, Mark. My last question, and then I'm gonna let somebody it required sharing a screen because I tried working this problem and from A to D, and it was just so time consuming. It's like, which of the following system will generate an inverted reduced image? And they gave you different focal length and different object length. Do we literally have time to do the equation for all the F and all the O's, or is there an easier way we could say, well, convergent lens, you told us they never have focal length greater than 0. Like, can I show you the problem? It's really simple.
Yeah. Let me see if you can share. Yeah,
it's.
Oh, you can share. But I mean, the first thing that comes to mind is actually, yes, you would do it for all of them, but I think that's time consuming. What you may be able to do is maybe after
Let me
like
see
the
if I'll
first or
copy
second,
and
you'd be able
paste
to
it.
notice a pattern. You'd be able to notice a pattern and then maybe figure out from there. But like the actual way to do it is, yeah, do each one.
Let's see if I could.
So what you would do is you would first you would find, if they gave you the object length and the focal length, you would, again, like I did, find the image length over object length to find magnification. Inverted versus not inverted is just negative or positive m for magnification, and then reduced is m less than 1, enlarged is m greater than 1. It's not, I wouldn't say it's as time consuming as you may think it is, but it does take a little bit of math.
Are all
While we're waiting, does anybody else have any questions?
do all divergent lenses
Sorry,
or virtual images? Could you clarify that? You said all divergent lens will give what kind of images?
no. All diverging lenses have an f as of a focal length, a negative focal length. All converging lenses, all converging anything has a positive focal length. As for real versus virtual, it depends on eye. So, and it's different, right? So like a positive eye is always I believe positive eye is always real and negative eye is always virtual.
Okay, so those we just commit to memory.
Mm-hmm.
Okay, thank you.
Okay. Does anybody have any questions? Any other questions?